Okay, let's summarize then how to do the calibration first. So if we have three kind of the method to get the contrast for the modulus and adhesion. So so if you only want to see then the mixed material, then just see the contrast. You no need to calibrate the probe. So the probe, the parameter, the probe, if no need to calibrate, just a contrast, Then you no need to calibrate. Okay, no need to calibrate. Sorry.
Okay.
Yeah, this one.
A.
So you no need to calibrate. Okay. So if you you need the you need the you need the modulus value, modulus adhesion. So you need the calibrate the probe. Calibrate the probe. Okay. So the calibrate the probe have the two kind of method. One is you no need the accuracy. You just use the probe to default parameter. So the default parameter, the one. Okay. Maybe. Okay. I think this one is better. Okay. Okay. So the parameter in. So the parameter include the probe diameter. Probe diameter. This one you can get from the website. Okay. Then T from box. Okay. So the deflection sensitivity. Deflection sensitivity. You can use the Sapphire. THE Sapphire. YE. IRE Sapphire. Use the Sapphire. Get a first curve. And get the sensitivity. From first curve. Okay. And another thing is you can get from select probe. Okay, so that's clearly right. When you select the probe, the deflection sensitivity provide you one value. That's the SBO factory provide you the value. And also if you cannot find the value, you can check the box. So the box have a L. The L means the cantilever length. So normally the deflection sensitivity is a little bit less than this half of the length. You can use that. Okay. Another one is a little bit less than the 2. Okay, 3 methods. One use the Sapphire to get the first curve. Use the first curve to get the deflection sensitivity. Another one is you can choose the probe. When you choose the probe, they have a data here. Okay, so this one is the factory to provide. Another one, if you really cannot find this value because the probe you bought from the other the other branch, then you cannot find the probe at this list. Then you can take the lines divided by 2. That's also almost similar with this value. Okay, similar like similar. Okay, that's not for accuracy. If you really need the accuracy, we should do accurate. Okay, then we need these three parameters. That's the first is 1, then deflection sensitive. Deflection sensitivity. The method is the sapphire. Is the sapphire. sapphire 那PE 人 IRE 人哦 SAPPHRE PP 2 PP is the sapphire. If you have the sapphire, then this sapphire must be very clean. Must be very clean. Then use this one to get the first curve. Then or you can use the calibration. Then calibration touch at here. You go to the PeakForce QNM touch. No, not this one. So that. Okay. Use this one. Just go to touch. Use this screen to get the deflection sensitivity value. Okay, this one is should touch on the sapphire. To get the first curve. Okay, so so after you get this one, then another calibration. Okay, I just show you this one. Okay, at this one, we should calibrate three parameters. The first one is the spring constant, the deflection sensitivity. Okay, deflection sensitivity, and also the kinetic distance QNM, and also we need the PeakForce tapping amplitude density. Okay, so all these three parameters provide you more accuracy the QNM value. Okay. So for both these three parameters, we need the sapphire and calibrate using the ramp the first curve. So the method is like this. Then another one, if your machine is multi-model, they don't have this screen. They don't have this screen. You just use the sapphire, put on the chart, and use the contact module or the first QNM contact on the sample ramp 1. Ramp 1 flow. So also can get the deflection sensitivity. So this one is the 1 parameter. Then get the sensitivity. QNM kinetic distance and amplitude. It's the 3 parameter. Okay, so this one for sensitivity. Then another one, second parameter is K. For the K, we have two methods. We have two methods. One is use thermal tune. Use the thermal tune. Then another one is the set method. Okay, so yesterday we already talk about this one. For thermal tune, if the cantilever P value is less than the 1 Newton per meter, use the thermal tune. If the cantilever is a triangle shape, is a rectangle shape, then you can use the set method. For set method, thermal tune. When you do the thermal tune, when you do the thermal tune, the probe must be left from the surface. Okay, far away at the tip. Far away, AWAY, from surface. Okay. So when you're doing this thermal tune, you also can record this then after thermal tune, you can get a key, and also you can get the Q. Then you can get the frequency. Okay, you can get these 3 parameters. Of course, frequency. Frequency, FREN, FREN, frequency, CU, CY, ENCY 是吧？QUENCY. Okay, you can get these 3 parameters. Okay, so so if you use the set method, if you use the set method, you can use this Q frequency. The frequency, length, and W. These 3 parameters. Just calculate. So it's quite easy, huh? Also this Q and the frequency, you can get Q, the frequency, Q and the frequency, Q frequency can get from typing module. Typing module tune probe. I think everyone knows how to do this tune probe, right? Okay. So after you get the different sensitivity, you get the K. These 2 parameters. Another one is the R. R is a little bit difficult. So R, if we get the calibrate R, let me do more. R calibration have the relative method. Relative method. CHOD. One is called the relative method. Another one is called the absolute. Okay. So all these 2 kinds of the method can get the R. The relative method have a different procedure from the absolute method. So if you use the relative method, okay, the procedure, the step, then can go. One is use the simple PeakForce QNM standard sample. Okay, use the standard symbol. Put the standard symbol first. Then put the center sample adjust. Then here PeakForce QNM. PeakForce QNM. Then scan on sample. Okay, scan on sample. Then when you scan on the sample, then adjust. Then adjust the period set point. So we control the force. The probe touch on the surface. The force is the set point, right? PeakForce QNM use the PeakForce to control. So adjust the set point. Then make the indentation depth. Indentation larger than the 4 nanometer. Okay. So then if the indentation depth is larger than the 4 nanometer, then you adjust R. Adjust R. Make the modulus value equal to the value on the board. Okay, so clearly. Then step 2. Then put your sample. Your sample, huh? Okay, so your sample engage it on surface. Engage on the surface. Not clear. 这个方便吧？看消不进去啊？哦，消不掉是吧？它会放的，它放面上去掉。哦 ，OK。Just copy this one to here. Okay. Okay. Then continue, huh? Okay. Okay. So this one correct. Okay. Okay. So the we write down again, huh? Relative method. Relative method. The first one, the first step is use the standard sample. Okay, use the standard sample. Adjust. PeakForce QNM workspace. Then use this workspace engage on surface. Engage on the surface. Then adjust the set point. Make the indentation. Make the indentation larger than the 4 nanometer.
So we check indentation channel.
Indentation
not
channel.
Deformation channel.
Deformation and indentation is same.
But the value is so
a little bit different. For the old older version software, it's the deformation. For new software, it's indentation.
New software.
New software indentation. Take the indentation. Indentation. The when you see the indentation is larger than the 4 nanometer, then adjust. adjust R, adjust R, make the value then equal to the box value. Okay, the standard simple value. TANB. Okay, so for this, this standard sample, the simple one is 2.5 megapart PA. Then the simple two is 3.5 mega. Then the third one, the simple three is 2.7 gigapart. Okay, these are all the provided the standard sample. So we have the simple four. Simple four is quite hard. The simple four is 72 gigapart. Okay, so if your sample is around 2.7 and 72, then you can use HOPG. HOPG is 18 giga. Okay, because inside the lip box we don't provide the HOPG. You can find the HOPG by yourself. Okay. Okay, so this one is how to we use the standard sample to get the R. That's the procedure. Okay, so another method is called the absolute method. So for absolute, okay, absolute, method. So for absolute method, we should use the simple 6. Okay, so this one is a little bit tricky. We always suggest you do your sample first. Okay, so when you do your sample, your sample first. Okay, when you do your sample, PeakForce QNM workspace. Okay, scan on your sample. Engage on surface. Okay, engage on your surface. Then, then after engaging your surface, adjust the set point. Make the indentation. Larger than the 4 nanometer. Okay, collect one image. Okay, collect your image with collect your image with the first curve. With the first curve. So when you capture this, when you do the capture, if you include the first curve, when you collect the image, if you do this one, so if we go to the scan parameter, this parameter. So when you see this one, it's a little bit different with the before the only capture surface. Here have the one have a tail, right? So this one is for first curve. If you clear this one, then this all these captures will include the first curve. When you capture with this first curve, you get the two images. One is SPM, is only for the image. Another one called PFC bar, then that will include all points in the first curve inside. Okay. After you okay, with this first curve, then with this image, then get average indentation. EEPTI. Okay. So that means that you get the indentation depth value. The means is when you do this when you do the scan, all the probe is this one. Okay.
Yeah.
The probe is not a ball, right? It's not a ball. So we don't know then where is your depth. So the depth is different, then the R is different. Okay, so because then the probe is like this. In the different depths, the R is different. Okay, yeah. If your probe is a ball, then the R is only one R. So there's no need to calibrate. You know the R. But for the probe is like this, different depths, the R is different. Okay, the R is different. So that's why we must know how we indent on your sample. So that's why we get the value first. Okay, we get the indentation depth value first. After you get this indentation depth, okay. Then put the simple 6. Okay, put the simple 6. Scan on this sample. Okay, scan on this sample. Then after you collect this, collect one image. So for this image, we request you use the 3 micro by 3 micro image. Okay, 3 micro by 3 micro image. The 2.6 by 2.6 data point. Okay, after you get this image, then open this image in offline. Okay, in offline. Then open this one in the offline software. We have the typo qualification.
Can I have an example here?
Okay. That's good. PFM.
And
PeakForce QNM. You got the
this one,
okay.
something like this.
Okay. Something like that, because this sample is quite hard, very hard. The means is this one is hard. Looks this one is like the sample, like a probe. Then the image is your probe. Okay. So after you get this one, then you use this flatten. You get the flatten first. Notation first order flatten. You get this flatten. Use this typo qualification image. Okay. When you get this typo qualification image, you get the depth. So just now we collect on myself the sample. We get the indentation depth. We can write here. For example, we get the 10 nanometer. Then you just quality. Then you use the estimate tip to get the value. So this value is on the 10 nanometer depth, the tip, the tip radius is 7.84. Okay, so this one is how to calculate your tip radius. You get this tip radius. After that, get the tip radius. You get the tip radius. Go back to your image. Open your image. The PFC. Okay, the PFC image. Then after that, then I know you get the PFC. Okay, okay. Here have the PFC file, and you open this PFC. Okay, so in this image, include all the first curves. Let me see. This first curve is not correct. Okay, so how can you see this first curve is not correct? So normally the first curve should be like this, right? But the first curve is like here. So the reason is when you subtract your background, the background subtract is not correct. Okay, so maybe later we extend the sample, then you can see this one. Here have all the parameters you should calibrate. Okay, should calibrate the parameter is this one, right? R. You just put on, you get the value from the tip qualification, put here. And after put here, you use the recalculate map, the modulus. Okay. I think you your modulus. Modulus. Because this one is not correct. That's why the modulus is don't have the don't have the value. I try background.
Yeah. So I checked it.
You get the first curve, right? So the background normally is tracking during scanning. During scanning. Okay. Go too much.
Yeah.
So that's the full procedure. Recalculate map. We get the recalculate the we get recalculate. Then the image, the modulus is your samples. So it's clear. It's clear. The procedure is like this, Okay. That's the fully calibration procedure for deflection sensitivity. Then for K, for R. After you get this one, then this one is for the calibration parameters. We also use another two parameters. Is POSION, Poisson POI SSON Poisson ratio. This for this for the RATIO, right? Okay. For Poisson ratio, is not calibrated for most of the materials. Is less than the 0.5. Is less than the 0.5. So and also in the formula we use the Poisson value is square, right? It's a square. So that means it's not not very big difference, even you put the 0.5 or the 0.3. So, so for most of the material, we use 0.3 for this value. Okay, that's the default. If you said your material, your material, you know the Boson ratio, then you put the value here. Okay. Put the value is for the offline software is the Boson ratio put here. Okay. And another value is called the tip angle, tip half angle. ANGRE 哈 another angle. For most of the brokers probe, the tip angle is around 18 to 19. So you just can put 18 or 19. Okay. So the angle is this angle is not the one angle. It's a mixed angle. It's have the front angle, back angle, then the side angle. We get it together. So we give this value just. So most we give the 18. Okay, this one no need to calibrate. So for probe parameters, from here we get the deflection sensitivity, spring constants, tip half angle, and the tip ratio and the Boson ratio. So all these 5 parameters to calculate the modulus. Okay, so that's how to calibrate the probe. Any questions about that?
So for relative method, yeah, if I really just keep the same set point for standard sample and
yes. So you use the standard sample with the PeakForce workspace engage on the surface or adjust the set point.
So the force on standard sample should be same.
No. The same is the indentation depth
so
is the same.
We control the set point.
We control the set point, make the indentation depth the same. It's not the set point is same. It's the indentation depth is same. So we calculate this indentation depth. Then adjust the R. Adjust this one is for relative method on your sample. No need. No, you just keep on your sample. Here have the okay. Okay. Now here less than one step. Then put your sample. Okay, but your sample. After you get that your sample, then same in the PeakForce PeakForce QNM workspace. The workspace. Workspace engage. Then engage. Then the adjust the set point. Then make the indentation equal to indentation depth equal to the standard sample. Indentation depth. Then you get the modulus image is your modulus is you want. Okay, so that's clear, always.
So if I use if its indentation become too large, so I even make a very small set point, and then we need to change the probe.
Actually it's like that. Okay, we have 2 methods we have the 2 modulus to simulate all the modulus, right? Then one is the Hertz modulus. One is the Hertz modulus, right? The Hertz modulus is use R, right? is from the formula is from this one. 一星减一6方 then 的根号2 square 2 then the simple indentation is 2.5, right? It's like this. This one is called the Hertz modulus. The Hertz modulus is only for the two elastic simple. That means it's no it's no the power loss. Okay, this one no power loss. The two material is for the elastic. So this one is much less than this one is less than R. Less than R. Okay. This is request. So if you the depth your probe is like that, the depth indentation depth is very big. It's large if this depth larger than R, larger a lot of the R. That means we only depends this one, this angle. Okay, so the formula will be changed. This one is no need this one, right? We will get the R how can say that I forgot the formula. I forgot the formula. So this one called the GTR. Snedden. Snedden. They call the Snedden modulus. This is the Snedden modulus only for the single first curve analysis, because in the image we use the Young's modulus. Young's modulus only fit is the Hertz modulus. So if your depth is quite bigger, then that means your probe is too hard for this sample. But for first curve, you can. Okay, because in the single first curve, we open the first curve. First curve. Yesterday we found the first curve, right?
Strange.
Can you go to the first curve?
I try.
You try that. So this one, this modulus is only for the Young's modulus. Young's modulus is only fit the Hertz modulus, cannot use the Snedden modulus. So that means it's
我们以前留的。
这个哈，这个吗？
你以前的那个对。那你
看看有没有？Okay, okay. So if the indentation depth is quite big, you can when you do this analysis at here you can change Hertz and Snedden. Okay, but in the image you cannot. Okay, that means only for single first curve, no problem. You no need to change probe, but for the imaging, it's maybe a different. Also, if your depth is quite bigger. Also, if your depth is quite bigger, it's difficult to take out from the sample. So the image will be lost. Okay, so that's the problem. So that's all the problem. Any question? If no question, we can one by one to do that. Okay, yeah. We can one by one to do that. Okay, so let's do one more. New slide. Okay, 好。Okay, so for the first curve, if you want to do the first curve collection method, okay, first curve. So we collect the first curve. Okay, collect the first curve. You can in the three kind of the workspace get one is contact module ramp. You can get the first curve, right? You can get the first curve. You can get the first curve. Then another one is scan assist. Scan assist ramp. Okay, you can get the first curve. The third one is the PeakForce QNM. Okay, so for the single one, also we have another one is called fast first volume. Okay, or you can get this first curve. This one, for this one, we only get the first curve. Single only one. You cannot use this one to get the modulus or the adaptation. You only can get the first curve. You go to the analysis one by one. And for this, the scan assist module is same. You only get the first curve to analysis. All this one cannot get the image. Okay, it's a single one. Like the Gordon said, he got the very deep indentation. Then you can use this one to analysis. Okay. So for PeakForce QNM and FFV, that's the first volume. This one can get the first curve, get each point. You can get each point first curve and also can get image. Okay, you can get a modulus image. Then this one is the same. This one can get the each point. And also you can get image. Okay, the difference is this one is faster, right? This one is faster. This one is slow. And also have a force control difference. So this force control in the edit set. Yesterday, Dr. Liu draw the image like this, right? It's a snapper. When you do the PeakForce QNM, this one is one circle must be finished. So in the some set, the force will be changed. So we use the feedback module to get the scanner up to the higher, right? So this one is use feedback. Use the feedback. You cannot not control every point. Same force. Okay. So because in the edit set, we use the feedback. If the error is bigger, we up all the cantilever, we up all the scanner to the higher value. But the force is real time force. Reduce subtract with the set point. You will get the error lower, then get the feedback to the set point. So let's use the feedback, but the FFV, you can control this one in the each point. with the same force because we use the force trigger model. So this one is the force trigger model. This one is the feedback model. Okay. So if your sample is like the cell, it's quite bigger, then the fast first volume is more suitable. Then if your sample is just a normal sample, then the pure force QNM is good. Okay. So but the peak force and FFV is suitable for the sample is elastic sample. Okay, so that means no viscoelasticity. If you have the sample is like a gel, what you put here, the surface will be changed. Sometimes it's changed. That's the viscoelasticity material. So it's a little bit different. So all the QNM suitable so QNM is suitable. The range is megapar to the 10 or the 20 GPa and elastic material. Okay. Of course, someone also use this one to the kPa, right? to the kPa. So if the material is elastic, we have another method. On Friday we were talking about DNA, nano DMA. Okay, they use this one to get the elastic modulus and the loss modulus. Okay, so that means this one have the power loss. So for the very hard sample, all the cantilever, the hardest one is the K is equal to the 350. So that's not enough to put like the severe, like a copper, like the metal material because it's too hard. For example, silicon, we cannot use the silicon to get the silicon indent. So that's the problem. If your sample is over the 20 GPa, we should use the contact resonance. So that means is we cannot get the indentation. So that's all the QNM suitable range. Okay, clearly. So that means if too soft, QNM is not suitable. Very hard, QNM also not suitable. Okay. Okay, that's all the QNM one, okay. So so the first curve where I write down there. Okay. Then this one is a new one. So for the first curve,我在哪了？我刚才热掉了吗？哦，对 ，OK. So that's the method This one from the single force curve is suitable to analysis and Hertz modulus and Schneid modulus. Then, but for the peak force QNM image, we only use the Hertz modulus, get the Young's modulus value. Okay. So the Schneid modulus is not included in the imaging. Okay, so that's me start then how to calculate this one. Okay. If we use the so this probe is golden load one the O Tesla probe is a little bit harder probe, right? It's 300 frequency, right? So it's a hard probe. Then first one, we need to get the which parameter? So the first one is the deflection sensitivity. Whatever relative or the absolute. First parameter is the deflection sensitivity. Okay. Then we want to get the you already here. Sapphire. This one is sapphire, right? So you just load your sapphire on your track, then just your probe setup. Setup is focus on the probe only. When you load the probe, go to the setup module. So in this step, only for the focus, okay, only for the focus. Then if here you see the laser, if at this one you see the laser, if at this setup screen you see the laser, that means the probe load get a little bit of problem. Okay, so sometimes of course then the probe may be problem. Okay, on the setup, because then when you load the probe, it should be should be parallel with all the background, right? So that's when the laser should be like this. So we cannot see the laser because the laser is straight, right? So if you see that, that's one. That means the probe load maybe a little bit problem. Okay. Of course, it doesn't matter. Sometimes it does matter. Okay. You after you get this image, then for the probe, for the probe is for the probe. So if the probe, okay, sorry, too ugly. Okay, okay. So normally all the probe is like this. Okay, for triangle probe is most like this. Okay. It's like this. We have two kinds of the different probes. If the probe have the O stat, the name is the O stat. The probe is here. The probe is here. So if you use the broker's probe, the probe normally is here. Okay. So when you load the probe, you can set this read cursor's position. For this probe, it's the O probe. That's why I put the read cursor on the top. Okay, because the probe is here. Then if you change it to the navigator. Navigator is for find the simple surface. It's okay.哦，高一点吧。Okay. Almost. It's far away, huh?对，哦，还有一点近。 Okay, almost almost here. Yes. Okay, this sample is a sapphire sample. So we focus on the sapphire sample. Then use this PeakForce QNM, or you can use the contact module, or you can use all the touch mode. Okay, so the different one. So someone said I more like to use the contact module. Doesn't matter. You just go to the contact module. For the deflection sensitivity, I show all the method. I show you all the method. Okay, we go to the contact module first.
Why?
Okay. Okay. So before you engage on the surface, change this one to the small value. Change to this smaller value. This value you should compare with this value. If this value is quite bigger, then that means you didn't adjust this read point to the center. Okay. Then the force just can engage on the surface enough, because this one is a quite hard sample. So I use the lens force to engage on the surface.说的你的镭射球太颗粒了。
那当天的针不是那不是新的针吗？
这是旧的针。
旧的针
啊，没关系，没关系。
对啊，
但是镭射有点太颗粒了。我let me create a folder 啊。Okay, after you engage on the surface, you just no need to scan image. Then you just go to the ramp. Okay, directly go to the ramp. Then use the ramp to see then how about the first curve. Then you just do the single ramp. So when you do the single ramp, you can see this one is quite long, right? It's quite long. That means here the data is less. So if you want to increase this data point, we can reduce this scan size. For example, we reduce to 200. You can see this slope area gets the more data point. Okay, you just capture this. Let me change. Let me capture file name. This one is. I think I can put to E driver, right? Then E driver, I make a new folder. Yeah. Um, 06. Okay. I get the capture file name. Then this one is the force curve. This surface. HY. Okay. Then let me get the picture. Okay, I go back here. I can get my further, right? Okay. So this one is only the 1 point. Sometimes if you engage on the dirty area, the curve will be not very good, right? So that's why we can collect a few of the different areas, the first curve. For example, if we go to the here, then we have the we have the XY scan. Here have the columns and the rows. We can use the different areas to collect. Okay, then we just ramp on the different area. So you see, like this kind of the images, we cannot use it because here has some loss, some pore loss. Okay, so that means some area maybe the dirty. Okay, okay. So which kind which kind of the first curve is better? Let me use the better one. So if the very hard sample, that means no any sample change, right? All the deflection from my sample, not from my cantilever, not the sample. That's why this one is trace and retrieve totally matched. Yes, totally matched. After you get this image, if you think this one is still longer, you can reduce more. Okay, if you get this first curve at here, we have the update sensitivity. Before you use the update sensitivity, draw these cursors from left side to the slope area. Then you get the update sensitivity. So this sensitivity is means from the software. It's a contact model. Now we can have the 19.2.6, right? Okay. Then if you get this value, if you want to use this value, just okay. So the value will be read to here. Read to here. That means you calibrate with the contact model. So after finish, you need a withdraw. Okay, you need to withdraw from the surface. This one is one method. One is one method. Because we collect the 5 images. This one from the real time. Because we didn't withdraw, right? This one from the real time. Even with the offline software, we have this function. Okay. So for example, we open one cursors with all the offline software is the same. If you use this one, then you just draw these cursors from left side to right side, get the slope area. Here have the command update sensitivity. So this sensitivity maybe a little bit. That's why we want you to collect a few of the first curve to get the average. Okay. So that means we collect the five cursors. This one is the 92. Then okay, we record this data. Then open another one. We open another one. Okay. This is a second. Okay. It's updated sensitivity. This one is 88. Then you can get the average 90 plus 88 divided by 2. Okay. So that's how we get the average the deflection sensitivity. Okay. This one is the one method from contact model. This one more accurate. Okay, this one is more accuracy. Then another method is you go back your the first QNM one. Then go back to the QNM. So slow. go to the setup. It's the same thing, huh? Then you get the setup, you navigate on your Sapphire surface. Go to the advanced. Okay, go to the advanced. If you need the thermal tune, then at here, because now the tip is not on the surface, it's far from the surface. You can get the thermal tune also. Okay, you can get the thermal tune also. Then no, they don't want to do thermal tune because here don't have the value. They don't have the value. Okay, we just touch on the surface. We just touch on the surface. Touch on the surface, engage it first. But with the contact module, you cannot not one time to calibrate the distance QNM and PeakForce typing amplitude field. That's only for the deflection sensitivity. Okay. Okay. After engaging on the surface, then here have the ramp. So if you want to check the ramp, the parameter, you use this extend this more setting. Here is the ramp size, and the ramp set point is for the force control. The force control is means the how many maximum force. Okay. So at here, if you just click this ramp, they will get a few 5 or something, 5 the force curves. Okay. The 1, 2, 3, 4, 5. Then the software will calculate this 5 force curves average deflection sensitivity. After they get the data, they write to calculate value. This one is the before value. Here is the calculate value. Okay. So after you get this value, then this value will be written down to the calibration deflection sensitivity. Then sometimes you need to confirm which frequency you will use on your sample. So if you want to use the 2 kHz at here to the 2 kHz, just then calibrate is the snack distance new QNM and the PeakForce. Okay. They will update this value for you. Okay. So update and verify current, and also you update this value. Then the calibration will be finished. Then now you can install. Okay. You can return and save. You can use the return and save. They will withdraw automatically.
Can we use this K value?
Is
accurate.
It's not accuracy. Okay. This is not very accurate. You need to calibrate yourself.
Oh.
Okay. This value is from the calculation. This one is from calculation because they change the deflection sensitivity. They change this one. They're from calculation. Then the P is more easy to calibrate because the P can from calculation, right? So now the second one you calibrate the K. Here give the 1K, right? Give the 1K. If you said just so you can use. Okay. Then if you want to use the more accuracy the K, just withdraw from the surface Now we have two methods, right? We have two methods. For this cantilever, the K is more than 26. It's quite bigger, quite hard, quite hard. This for hard the cantilever, which method we should use? Set method. Use the set method. We use the set method. We need the we go back here. Okay. Now we go to the calibrate K. K. Okay, we should calibrate the K. K have two methods. One is a set. Is a set method, right? Okay. One is the thermal tune. But for set method, we also need the thermal tune because we need the parameter is length W and F frequency FC, frequency and Q. Where we get the frequency and Q, we can get from thermal tune. Right? So how do the thermal tune? Is the frequency the cantilever is here, then you can directly go to the scan parameter. Okay, go to the scan. When you go to the scan, here have one column buttons. So this button called thermal tune. Okay, this one is called thermal tune. Just clear this thermal tune. Then at here have the thermal tune range. Because this cantilever, the first resonant frequency is around 300. If we choose 1 to 100, may not include, right? So we can use the higher one, with 5 to 200 kilohertz range. Then at here, you have a little bit of parameters that you should careful. One is the temperature. Because if this room is 30 degrees, you put the 20 degrees, maybe a little bit different. Because this one from thermal tune, thermal tune, noise thermal tune. So we should check the parameter, the temperature inside this room, and also the diffraction sensitivity correction, the value you can get from on the PPT for this value. Okay, different cantilevers, this value is different. Okay, and another one is PSD band. Okay, other parameter doesn't matter. Only this temperature and this correction efficiency. Okay. Okay. After that, you just accurate the data. When you do this accurate data, never about let this collect data finish. Okay. After you get this curve, you can see this peak, right? This peak is the first order listener frequency for this cantilever. You use a control, then use this control one, then draw a zoom in. Then you can use this cursor to find the frequency. Okay, so when you draw to here, the frequency should be the cursor here. It's 259. Okay, that's all the frequency, right? And also here have the Q factor value is here. So record this value. So this one is 259.3, right? 259.3. Then another one is 322.13, right? Okay. Open the box. Open the probe box. Okay. So check the box. L.
Oh, L. Person for one.
L.
Yeah, not sure.
Okay. Oh, so this one is Olympus the probe. That's why they don't have the lens and this on this box. Never mind. So if you cannot find it here, you can go to the website to check. Okay. Oh, okay. 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 So at here, the box have this one is 150, right? I cannot see clearly. I cannot see clearly. Sorry. The word is too small. Okay, you can write down here. Okay, this key is L is 160 micro. W is 40 micro, right? Okay, you need this 4 parameter. Then go to your your iPhone. You go to your iPhone. If your iPhone is not Apple's phone, then if you use the Huawei or other things, you cannot download the set method. If you cannot download with your phone, then you can download on the website. Then with your computer. Okay, so you get the smaller program. They call the set method. You just open this set method. So with this set, here this one. Okay, so you can see with this program, a few of the cantilevers they already put here. For example, AC 160, AC 2000. This one all the Olympus, Olympus, and the AD 2.8 Dama. Then if your probe is this one, you just clear. Okay, if your probe you cannot find the probe is here, then just go to the rectangular cantilever, because all the cantilever have the two kind of the shapes, right? One is the rectangle one is 三角形叫什么？ triangle. Sorry. One is a triangle shape. This one is a rectangular shape. Rectangle shape. You just choose this one and get the precise. Get the length, right? Length 160. 160. The width is 40, right? 40. No need to give the unit. They already have the unit here. Okay. And the frequency is same. Frequency is 259.3. And the Q factor is 322.13. Okay. All these parameters finished. Here have the calculate. Okay. 26. 20.6. Okay, so the key value is we get the key value is 20.6, right? Okay, so a little bit different with you provide the value, right? So we use this one. Okay, after you get this data, then you can return and save. Okay, return and save. Where the parameters we should write down to here. Okay, so this one is we already give a calibrator, right? This value is our calibrate value. Then here you write down not the 28, is around the 20.6. So let's finish the key. Okay. After you get this key and this deflection sensitivity, you can see here your set point is already changed to the nanonewton. Okay, so if this data is 88, 2.9. Okay, then if this one is a 1, if you didn't calibrate this value, so here only give you the milliwatt or the watt. Okay, so you cannot change here. You cannot change here. So if you want to know how many force, you must calibrate this value. When you give this value, this one must have the unit 2.9 229 milliwatt nanometer per watt. Okay, so if you change this one you can directly get the force. How many force? Okay. 我们休息10分钟。
Okay.
We take a 10 minutes break. Then you can drink some water or something. 这个洗手间的。Okay, so let's start to calibrate the arm. So we have two methods, right? The first method we use the relative method, We use the relative method. So if we use the relative method to calibrate the R, the first one we should change the probe, change the sample. Then we go to the navigate, change the sample. So this probe is around the 22. P value is around 22, right? It's quite hard. That means that this probe we can measure the gigapart material. So we use this one to measure the gigapart material. Then we use the third sample. Okay, we use the number 3. Okay, we use number 3, sample number 3.昨天你的推字儿这个哈，number 3. And we can take out this one. 哎，这个收起来。哎，这是这个里头啊。你这个是，这是撒菲尔是吧？这不是撒菲尔吗？是啊。4金牌的撒菲尔，给你放在这边上。OK。So the number 3 code the name is poly oh, I cannot see clearly. And this poly opcon. This may be a little bit hard polymer. Okay. I'm really know then what's the material for this sample. It's same thing. We need the focus on the surface because this one is also quite. This is so hard. Okay, here is the surface, looks like this one, the surface here.哦，哎，没关系，其实已经有了咖啡了，有咖啡了。哎。Okay, so the probe is here. Then you can see this probe. Then you can go back to the surface. So here is the surface, huh? Okay, here is the surface. The relative method is engaged on the sample. You know the value, right? You know the modulus value. Then you can take this parameter. Now we want to calibrate this parameter, keep reduce. Then this one is already done. Then the different sensitivity done. We only have this value, isn't calibrate, right? So now is you just engage on your surface. At here, you can see here is the scan assist auto control is already individual. That means this one for the set point you can control by yourself. You can control by yourself. Okay. So normally, if you just want to see then the topography, then this one you can use the fully on auto control on. Okay, at here we have another after calibrate the parameter is called the synthetic distance QNM. Before we already calibrated, right? So this one is that. Then this one is that. At this set, if you use the simple module, you only can see less the parameters. So after that, then you can just engage on your samples. For this sample, everywhere should be same material. So you no need to scan the bigger area. You just scan the 700 nanometer should be enough. Okay, so you just engage on the surface.喂，对，你说，你说相关售后的问题，你加我一个微信，我下了课我把那个我们的工程师推给你，让他帮你解答，好吧？好19910297813。好，你加我微信，然后呢，把你的信息发给我OK，好，Okay, so we engage on the surface. Then the first thing is to see this image, to see this one, this value. Okay, so this one is the indentation depth. If this indentation depth is negative, that means your calibration may not good. Or this probe is too soft for this material. Okay, so actually we need this the sample have the indentation depth. So you can adjust this one, adjust the set point. Okay, we go to the extend module. You adjust this force. Make this value is bigger than the 4 or the sometimes it should have the 4. Okay, then you adjust this force to make this one. It's bigger. If this one is doesn't change, whatever you change the force, this one doesn't change. That means the probe is too soft for this material.
Not too soft.
Yeah, that means you cannot make the more indentation. Okay. So actually, if you see this one is a little bit changed, is more than the 2 nanometer, maybe it should be okay. Okay, that means it's okay. Let's see. Okay, so if you get this one is already the bigger one. Okay, now is already the 3 nanometer. Already get the 3 nanometer. Later change this R value to make this one. This one is so we get the 0. For this sample, it's 2.7 giga, right? 2.7 giga. So we should change this one to make this value to the 2.77 giga. It's still bigger. Now we are calibrating the chip radio. Still. ？AD，我们是要找那个接入完名，要确定，不是现在这样是确定我的这个 tip radius 是多少，因为我的 formula 里面是要用到这个 R 的呀。这个真没有，这个真是那个谁的这个旧真啊。这我用的不是他的这个 calibrate 过的这个，我用的是不是谁给我这个针里面是没有的，没有校准过的，这个才是校准过的。So this one is calibrated by my factory. So after they calibrate, they use the QR code to record that. For this kind of the program, they never calibrate. So you cannot see then the code on the box.
This one is cheap.
Yeah. This one is expensive. This one is cheaper. And also inside this one is 10. This one only 5.
So we are calibrating the tip radius because we don't know the radius of the tip.
Yes. You can get the tip radius on the website, but it's social data. It's not accurate. It's not accurate. Yeah, and also that's why it's for the new program. But for this kind of already used the program, you never know. So that's why you need to calibrate.
So just if once we calibrated it, for the next time we use it, we just input the data.
No. The usual
every time.
Yeah. After you change the program, you should recalibrate. But the R you no need. If you get the R,
the same one.
Same one you can use the same one. But the different sensitivity you should recalibrate. K no need.
K and R.
But the different sensitivity you should recalibrate because if you put the laser here and here, it's different.
It depends on the position of
yes. So how do you know the data is around here? Then you can see this profile. Because now this profile is around 5, right? So you can add the more. So sometimes the data is quite funny. Okay. You feel the
isn't it very large?
Yeah, of course, because it's a relative method. It's not this method is a relative method. That's why the data maybe get the bigger or the funny.
So this is not the actual size.
And it's not the actual size. And this is from the relative one. It depends how deeper your invitation. Okay, so I think I can get the more invitation. Yeah, almost 4, right? Almost 4 nanometer. Oh, okay. Okay. Almost almost 4 nanometer, right? Indentation depth is 4. Then the we maybe this is too much. Let me see. Okay, should be add. This probe is used, so we don't know then how many data. So difficult to change to the 2.7, right? 2.7. It's quite difficult to get the 2.7. Wow, so big. The data is so big. Yeah, the value is a little bit funny, right? But depends because the sample you already changed something, we don't know, right? Because the sample is inside the box a long time or something. Okay. Okay, maybe I change one more. Oh, almost here, right? Almost here. Then how do you know this average data? You just collect one image. Okay, you just from top to down and collect one image. Okay, here you see this one is all the false. That means the false is already very hard, right? Yeah. We use so hard the false, we only get the indentation is 4 nanometer. That means this sample is quite hard. Then the probe maybe solved. Okay. So if you find like this, you should change a little bit hard probe. So this probe is 22. You may need to change to the 40, 80. The key value is 40, 80 probe. You may get the better result. Okay. So that's how to calculate this one. Then you just from the top to down get one image. You collect this image, no need this first curve. You just collect the image enough. Okay. So if you collect the full image, you use this one waiting for it down. So if you just collect the a little bit, because I already know this depth is around here, then this the force is around here, right? Okay, I just capital no. After capital no, then open this image. Open this image to take this the indentation one. Okay, indentation. This indentation, that means okay, all the force is changed. That means it's not keep everywhere here, right? A little bit changed, but we can get the average data. Okay, that's me. Let me read scan from top. So I capture now. Then I get the depth, indentation depth, indentation. Okay, so this indentation you don't do the flatten. For the property images, never do the flatten. Okay, only height image do the flatten. Okay, so you get this this one is the adhesion, the indentation. Okay, I get this indentation. I use the roughness analysis to calculate the average. So this average is 4.39. So the depth, the indentation depth, average for this area's value is 4.39. Okay, this one is average. Then the modulus. Average modulus is 3.49. That is bigger because this program maybe too soft for this one. The the standard value is 2.7. We should adjust more like this one get to the 2.7. Okay. So but for this one is already too high. Okay. 2.7 almost right? Almost. Okay. So after you change the parameter, you should collect the image again. Collect the image again. So no need to collect the full image. Just can get every age in. So you get the capital now, and we see the indentation depth. Indentation depth. So the roughness is 4.7. Then modulus. Modulus is around 2.8. Is almost right. So this R is all get the reference R. So after you get this one, visual, change to you want to measurement things. Okay.
So this is the standard.
And this is standard. This is inside this box. Okay. If you bought the PeakForce QNM function, you get this box. Okay. So this box have the golden one is have the HA. Then they have 6. The two boxes have the 6 this sample. Oh, beautiful. Okay. They get the 6 boxes. Then if you the PeakForce QNM no this HA, just the PeakForce QNMK, they have the 8. So one box have 4. Okay. So so you can see 1, 2, 3, 4, 5, 6, 7, 8. Okay. So another one have 2 more. Another have 2 more. This one is only the 6.
So how can we quickly select the suitable probe?
Okay. So if you want to do the PeakForce QNM for your sample, the first thing is go to the website, check your samples the Young's modulus range. So for example, is your gigapart. Then you should choose the probe is like here. Well, no, the website is internet. Yeah, internet. Because we don't know your samples. How about the Young's model for your sample, right? So that's why you should get some data from the website. Maybe a book or something doesn't matter, right? You get the value. Then that's one not correct, right? That's not accurate. It's only the range. So when you choose the probe to image your samples from here, okay, then we have the experimental guide, imaging module. Imaging module, we have the nanomechanic mapping. Then at here, they are introduce you how to choose your probes. Okay, what's the key? Then option key. The probe select. Okay, then this one is the order. The probe. How to choose the probe? Okay, you open this one. They told you then how about the materials Young's modulus range, which kind of probe is suitable. Okay.
But we don't know what is the value of the.
This is only for range. This one is only for range. For example, if your samples the range is less than the gigapart.
But I don't know.
If you don't know, then but you have you may have the think about is like the metal that is a polymer that is a cell, right? Huh? This just a reasonable just reasonable metal. Okay, like that. So So for example, is like the bare left stent samples, more is less than the mega part. Then you can choose the very soft probe. So for broker ones, then they provide 3 kind of the probe. Okay, so this probe, like this probe, that means this one no calibrate. Okay, you don't know the R. Then if here is have the dash, this one means it's the calibrate the R already. So for dash, that means 30 is the diameter around 30.
Diameter of the tip.
Diameter of the tip is around 20. Then dash 125. That means the tip diameter is around 125. This one is the calibrate. How can you get the each one the data? You go so for example, you get this code, right? Instead of have 5, you see this one is the dash 30, right?
Mhm.
That's not means everyone is 30. Each one have a different. Okay, so you can get this code. How do you get the code the each one? So go back to the here. Go back to here. Here have the code reader. Okay, so you see here have the scan QR code. You just open this one. So each one's parameter will show you. So that's why this one is expensive. Okay. Okay. So this one is how to read the code. If you install this one, this have 1, 2, 3, 4. This number is from here. Okay. You must remember which one you use. Okay. That's correct. So at here you can see the T. Then tip radius. You see this one is a different probe, have the different tip radius. So then the tip half angle they give the same, right? Then the Q factor is also different. Then frequency also a little bit different. Yeah. But for this kind of probe, factory no calibrate for you. You must calibrate. That's the reason. Okay, that's the reason. Okay, have any question about the relative method?
So if we use this the ordinary this one.
No, that's
yeah,
this one.
If we get once we get this parameter, we can use it for the next time, right?
Yes. Yes.
Okay.
Yes. Okay. So that's
So we spend time and then we earn the money.
yeah. You spend time, you need the money, and also sometimes or the sapphire or the standard sample get dirty or something, you cannot get correctly really the data. So they use the very good the samples to get the values. Okay. So that's why sometimes you get the parameter is quite funny, because of the quite funny value.
What is the minimum diameter possible?
The is for this opportunity method. It's around 100, 200. Always can get that. But most is depends the depth. We can get 20, 30, 40 like that. Most is 20, 40 something.
20, 40 diameter?
Mm.
Diameter?
That's the new one. The new probe is we call the different. That's a different different probe have different diameters. So for example, we have the new probe. If the probe is a silicon probe, if this probe is the silicon, it's a etched silicon only, like the SNIR, then the RTSPA, this kind of probe. If the new one, they never opened, then the website will provide you this value is around 5 to 10 nanometer. Yeah. It's a silicon one. Okay, it's
So
this
which
one.
diameter, like the tip or this area?
No, this one, this area.
Okay.
This area.
So what about this area?
This area we didn't provide you the email the value, but
What is the length of this?
this length you also can get on the website. For
Okay.
different probes, this length is different. Most of the probes is 8 micron.
8 micron. Okay.
8 micron. Then this for 8 micron for most of the samples is enough. But for some bigger samples, for example, they are like the cell. So this height is already over the 8 micron. Then your probe go to the bottom, then your cantilever will hit on here. So then you cannot make the correct image. So that's why we have the higher values probe for cell. For cell, this one is around the 17 micron. So this probe called the cell probe. This one for cell. Okay. So that depends. Then if you use your sample, it's quite soft. You cannot use the very sharp probe, right? So for this one is 5 to 10 nanometer. 5 to 10 nanometer. Then your sample is quite soft. Then we push go inside. Right? You cannot do that. So for this soft sample, we should use the diameter is a higher one. That's why we have the probe dash 125, right? If more soft, even this 100 nanometers probe is also cannot get. You should get the bigger one. Right? The bigger one they call the small ball probe. So this probe is not silicon, it's a ball. It's a ball. This one value is fixed. If you pass one ball on the cantilever, so this one is most of this one is a field of the macro. A field of the macro. Then even the ball cantilever ball probe have the 10 macro is more popular. If you already know this one, doesn't matter, right? You know this calibrate. If you bought this probe, they will tell you then how about the ball diameter. Okay.
But if my feature size is very small, if say 100 nanometer, and if there is a soft material underneath, under the feature, then how can I like measure it? I think.
And then you can draw that.
So this is a
A
100
deeper
nanometer.
trench.
Yeah, deeper trench, and this is the soft material. Here is the soft material.
Okay.
And this is around say 100 nanometer.
100 nanometer. Then how
And
about the
this
width?
is also 100 nanometers. Then how can I measure? Like this is soft, so
This
I
is
cannot
soft.
use this one.
You cannot use
I
this one.
cannot use this sharp
Ah.
tip, right? I have to use this one, but in the deeper trench, I cannot use this one as well.
For this kind of material, it's very difficult to get the modulus. You can get the depth. You cannot get the depth and the width. Then if you go to the PeakForce QNM, this one is quite difficult because
and
the probe.
Another problem is like say after this there is another trench, so it is kind of suspended here. So is it possible to measure?
Not possible. Not possible. You get the feature okay. If you just use the FID probe, the probe should be even the probe cannot be like that. You should use this kind of probe, then to get the deeper change the feature. If you want to get here's the material property,
So,
we don't have
so
the
if
probe
we
for you.
okay, if we use this feet, then what will be the distance? Like the so the feature will be like this.
And you draw more.
So this is the middle part, right? The material. So if I use the FM to measure the deepness, so the feature will be like this. So here is the material, or like this, the material will be destroyed and we'll get the whole trench.
If here is open, this one no material.
So there is a material, say very soft material.
Very soft. If you use a higher force, the probe penetrate go inside, you can get this one. If you use a very small force, you may get this one. It depends then how many force you use.
Okay, so I need to calibrate the force.
This one is for the depth. You know the depth, right?
Yeah, I know that.
You know the depth.
Yeah.
So you depends then your image is to see then the force is here or the force is here.
Okay.
That depends. Okay. That's quite difficult, right?
Okay.
Okay. That's how we the choose the probe, if you forgot about then this one, then you just go to your the website. Okay. Where the website? Here. So go to your the machine, open the help. All these menus is listed. Okay. So this one is the no calibrate soft probe. Then this one is diameter around 30. This one is diameter around 125. Okay, so this one is for frequency range. Because this one is quite soft, we no need to use this one for typing, right? But this one we sometimes use typing, so we should know the frequency. We tuning when we do the tuning, we can get the frequency, right? So this probe frequency around 40. This probe frequency around 150. This one is for frequency. This one is for diameter. Okay. 40是 frequency. Okay, so you see, if you want to measure then the gigapart, we should use 300, even the more, even the 525 probe use the giga. So that's why just know the probe maybe 2,000 for this giga. So that's how to choose the probe. If you the material over 10 mega, you should use the diamond probe. This one is truly diamond. Okay, is used here in cantilever 1 diamond. Okay, that's all.
如果你用的是这个，然后测出来的数据是其他的，那就稍微预测。
不看这个，看力曲线，看有没有压入深度。
只要压到深度。
有压入深度，你看有的时候你的压入深度你会去看的时候 ，so for the first curve 如果你没有压动的话，你的转到 separation 的时候，这是一条直线，它是这么直的这么下来的，这个地方是个0，所以在that means no indentation depth. And also if your calibration is wrong, for example, the diffraction sensitivity is too higher, then you may get like this. That means the indentation depth is negative. Indentation depth never should be the negative, right? that means you get the wrong calibration. Okay, so if you go to your first curve, this one you see this one is the indentation. We get the separation, right? The deepest point is 0. That means then we get all the indentation depths from here to here. Okay, from here. So how do you calculate the indentation depth from this baseline? This one is the baseline, right? This one is the baseline, right? This is air, go back to air. Then from here, extend this one to this curve. That means the probe should be, they withdraw from here to here, should be left the surface, right? Because the adhesion, they cannot go back, but the here should be the top one, right? So the depth should be from here to here. From this extend to here, then you can see from here to here is your depth. Okay, this is how to measure indentation depth. So if you your depth is quite bigger, it's already to here. That means not suitable for the Hertz model. That should use the Sneden modulus. So Sneden modulus and the Hertz modulus, they give the modulus is different. Okay. So you see, if your depth is already negative, that means not correct, right? So for example, we use this one. We use this one. See. So you see, this one is already here. Here should be the 0, right? Here be 0. The depth is around here. That means you not to change your sample. Yeah, this depth is 0, that depth is 0. That means no any simple deflection, right? So that means this problem is solved. So it's not. Okay. So now you can change your probe. You should change the probe. If your sample, okay, we got one sample. We never know then this one is softer or harder.
Yes.
It's a new material.
Yes.
It's a new material. We don't know, right? Then use the 300 volt RTSB. The middle one. Use the middle one to test first. Okay, you load this probe. You test first. If the depth a little bit force set point, you change a little bit the set point. Wow, the depth is already 100. That means the material is soft. Then you change it to this probe. Okay, if more hard, you change it to this one. Okay, so that depends. If you never know, you just try from middle track. Okay, clearly.
If you have the probe on hard materials, it's harm to the probe.
Yes. You see, if your material is very hard, you must use the hard probe.
Yeah.
This one is hard.
The probe will be the probe itself. Will it break the probe?
No. So actually for AFM, it's difficult to the broken your cantilever because the cantilever will be bending. So but if you give the very hard force, that also can break your cantilever, right? So how do you know you break your cantilever? You control the force. Then you control the force. When you control the force, when you get to the ramp, you get the ramp. This one is you control the force. This is the maximum force. You control that. If you give this value, it's very, very hard. Of course, they also. Okay. OK.
老师，这个是最大点吗？
哪个
是加的最大点，
这是最大点，到这个点我就停了。
就是最大就是这么多吗？
不是，你可以加呀，就像他说的，我要加，他可能不用停了，对吧？
施加的力嘛。
这是施加的力，就是最大点那个力。到这儿就停了。
还有一个就是之前说有个set point，那个和最大力全是关系。
这个是，你看啊，你看你们又给混了啊。OK 好，我这个 trigger 的时候，就是我就一个 first curve 的时候 ，one first curve we use the trigger force， 这个最大 point。OK we use the trigger。So the means the trigger means is you get this value. So doesn't matter where you are, you get this value. No. Okay, but for set point, this one is called trigger, no feedback. Okay, no feedback. The set point is when you scan on your sample. When you scan on your sample, this one we go back scan, go back scan. So when you go back the scan, this one is a set point. This one is a set point. Set point means is we give you a default value. If you over this value, you should come back. Okay, let's use the feedback to control. Use the error. Okay, use the error. Use the real time or your force. Your force is 70. Now is over this set point. You should reduce. Reduce. We use the controller inside the controller. The PID feedback to control that. Come back or increase all the distance. Okay, I can give you one example. For example, is a ball. This ball 那个气球叫什么？bubble 哈？balloon. Okay. If you have the balloon is flat over the 100 kilometers. Okay, then they flow. If this one is flat, it's all doesn't matter. Come to here. Okay. The force will be changed, right? Here is the force will be changed. Then you must give the power like the flow to up, right? Correct. Then up to your head. So you should keep the 1 kilometer from your head. But when you give the power, maybe higher, maybe lower, cannot really get the 1 kilometer for your head, right? So you should add power, reduce power, add power, reduce power. Then finally get 1 kilometer from, then fly again. Right? That's called feedback. That's called feedback. So when you see the scan, the scan parameter, you always have the gain value. At here is not really clearly this one only the one gain, but go to the contact module and the typing mode. You will do PID feedback. You see here. Okay, you see. Always we have the deflection set point and the P gain and I gain. That's for feedback. Okay, so
这个实在是听不太懂这个英
对，
语。
但它那个 feedback 它是怎么确定的呀？
啊，
它是测试的时候它自己去。
我们一直在监测这个力度。
对，
一直在监测这
然后
个力度。
跟着那个实际
跟着这个实际，你看啊，你的这个探针是压在你的这个样品这个表面的，我保持在一个恒定的力，对吧哈？如果是 flat， 我就这么走呗，这就叫咱们一个 probe， 我这么压过来，我是恒定的力嘛。到这个边界的时候，这个力就不恒定了，对不？它就突变了，是大了还是小了？ 对吧？那一定是到这个地方就大了嘛，对不对？这力大了，大了有，可是这个力大了，说明我们的这个，我就监测我现在这个力大了，我就跟我现在这个力去比较，有个差，
有个差，
对吧？如果是大了，哎，
设定的值有个差，
跟设定值有个差，然后呢，我把这个差呢就给到我的反馈系统，哎，我要让它啊说它大了，说它大了呢，我的 scanner 就得往上抬，对不对？
那减小
啊，咱让减小这个力，减小一边减小一边跟着比较，一边减小一边跟这个值比较。
哦，
到了它了，我就再继续。
到了什么？
啊，到了这个值了呀。
到了设定的值
啊，到了设定值啊。
这个就是 set point
啊，这就是 set point 的作用
和 feedback
和 feedback 啊，听明白了吗？啊，就是你看刚才我给你们举个例子啊，我这气球这么飞，对吧？这是1公里，对吧？这是1公里。
高度你是按高度？
我是按高度，对吧？我本来是在这里的时候是1公里，我这气球这么飞，到这里的时候，到这里我气球必须得上来，对不对？要不然就力太大了呀，就撞上它了呀，对不？那我就跟它比较，这1公里就保持不了了，对吧？到这不就0了吗？那1公里就是我的 set point。然后到这里的时候，我的 set point 就控制不了，成0了吧？
对。
不是我的那个高度到了0了，对吧？那我现在就得要升变起来，对不对？我就然后到这个高度，我再保持1公里，然后再走，哎，那这1公里就是 set point。那到这个地方抬是怎么抬的呢？就是我的反馈让我的
feedback 说它是0，它不是1000。
对，
所以 feedback 让系统让它
抬起来啊，然后那个是我的控制我的扫描管，就让它抬起来了，对吧？抬起来了，到这里的时候，它抬的时候抬的这个过程到底是不是1公里？你不是得检测吗？对吧？啊，抬得高了还是低了？抬得高了还是低了？对吧？你是不是得检测它呀？所以呢，你就有一个反馈，就是爱干是增加了、减小了、增加、减小啊，爱干和不干的这个过程。那昨天刘洋讲过这个了呀，
但是我
没听懂是吧
？set point 是一直调节，然后所有
不 set point 是定值。
所以它如果一下子突然力特别大的话，
有
可能会撞坏。
对呀，所以做 scan 和 sys 就是这个 peak-force QNM 有时候不适合起伏特别大的样品，就是我的抬高的高度就这么大，这个定值，但是我的力曲线我是可以抬很高的，我可以抬很高，听没有？你看啊，这个里头 ，OK， 你们看，在这个里头，这个 force 啊，这个 peak force 里面 ，peak force 有一个振幅，对不对？这个振幅最大的在这个机器上只有300而已，不能太大了。
振幅
就是只有300纳米啊，只有300纳米。如果你的这种起伏特别大，我就这个超过了，我就有时候就抬不起来，回不去了。然后呢，但是我们的力曲线是没关系的，我可以远远的下来，再抬回去，那个就是慢嘛，所以就慢了嘛，对吧？我下来再抬回去，我这个是 ramp size 是你可以给的，咱们刚才 ramp size 多少？600，对不对？你可以增加吗？增800可以吗？增1个微米可以吗？增2个微米可以吗？都可以。
就说那个256×256这个，就是说我们需要展示在文章中，应该是跟这个 ramp size 没有关系，只要是256×256。
不是，你的256是扫图的时候，这个他弄混了，他把参数弄混了啊。OK， 你们这个参数现在是有两套参数啊，他弄混了。OK， 这个参数这一套里面的参数 scan and 或者 take parameter 里面参数是扫图参数 ，OK， 是扫一个 area 的参数。
这个是扫图的参数。
这是扫图参数啊。
你看那 scan size 就知道。
OK， 这是扫图，比如说我扫个5个微米，对吧？我扫5个微米， 我拿到的这个图呢是5个微米的图。这件事怎么这回是高级培训呢？会OK，来我打开一个图，啊。OK， 你看到啊？刚才的受的那个参数是扫图参数，听到了吗？在这个里头是扫图的参数，扫图才用了 feedback，OK， 才用了 feedback， 我才去比较 set point 的这个 feedback， 然后这个力大了，力小了，是吧？哈，我去反馈它，在某个点去反馈它，然后呢，这个拿到的是在一个区域里头的。对不？因为我扫数据，一会儿高了，一会儿低了，一会儿高了，一会儿低了，我才有反馈，对吧？我才反馈。好，那这个里面给出来参数，给出来的是图，最后你拿到的是图。OK， 拿这个图，首先第一个参数是什么 ？area， right 哈啊 area by micro by micro 啊 10 micro by 10 micro， 然后这个里头用的是 feedback，OK， 这个里头用的是 feedback。干嘛哈？干和 set point， 然后他说的这个256乘256指的是什么呢？我先在这个图上面，这256第一个256 simple per lines， 第一个256是在这一条线上我有多少个数据？data point 在一条线上，然后呢，第二个256是这个 lines 扫了多少条线？听明白了吗？这扫了多少条线？如果更加的这个清晰的我给你们看一下这个图的这个线，看到没？这个线就是这么一条一条这么扫过来的。OK， 这是对面来讲的，对一个 area 一个 for one area 来讲的。所以呢，你看我们扫描就是扫了这么多条线，一条线一条线的扫过，然后把这条线上的这些数据做成图，就是我的3维。你听明白了吗？
老师，那我们这个没有涉及到
ramp 是只到一个点上，我在这上面选了一个点，我取 ramp 是没有，这时候的 ramp 是不成图的，它是一个点的数据。
那个 force，就是说力曲线的这个是指的
是一个点，力曲线只有一个点。
但是不是可以画一条线，然后就是有很多个点，然后都可以抽取出来？
那是抽出来也都是单个点的力曲线，那个没有成图，那个是因为我 save 了每一个点的力曲线。你看啊，这个，你看那个Golden说的这个图，这个叫 PFC， 我每一点的力曲线都有，看到没？比如说我现在是我选择3个点，这就是3个点的力曲线就出来，看到了吧？所以这个力曲线是我在 capture 的时候，我把每一点的力曲线也都给存了下来。OK， 如果你没有这个力曲线，你这个是没有办法重新，你比方说改了数据，我是没办法重新 recalculate 的。那你这些力曲线你都可以 export 出来是个单独的客户，比如说这我选了3个点，看到吗？然后我 save 客户，你看我 save 这个客户，我 save 到我今天的这个里头来。我存到 E driver 啊 ，OK， 人家那几个人给走了是吗？不是你们刚才说英文听不懂，所以人家就走了啊？OK， 来看着哈，来我把它放在这个里头，然后呢，我现在选了3个点，看到没？然后呢，我去看我的这个里头的时候，我就应该有我这3个点这个数据。按这个啊，来我去找啊，是 E driver 里面是吧？E， 我存到 E 里头了吗？不是 E。哎，E 我的叫这个，看到没？这就是这3个点呀。 这是3个点的数据啊，是咱们在刚才这个地方上打开的这3个点啊数据，这是一个点一个点的数据。你就记得 AFM 有2种功能，一种扫图，一种排谱，所有的谱都是一个点一个点的数据。OK， 那你说你不是你这不是也成图了吗？是因为我把每一点的都记录了下来，然后呢，再让它成为一个。
它厉害就厉害在它效率很高，
就是离线的时候，我们可以分析任何一个点。
对呀，而且你还可以重新分析你的这个 model。OK， 你看刚才不是说，假如说咱们现在把这个东西给重新 calibrate 了，对吧哈？重新 calibrate 了，我的 model loss 到底是多少？比如说我现在重新跟那个 calibrate 完了，我的 T-value 是100。我看这个，因为我存了这个原始数据，对不？好，那我既然存了这个原始数据，我 recalculate， 我把我现在的这个数据给了你一个反馈的过程，听到了没有？听到了吧？啊，然后呢，我现在把这个东西弄进去，我 recalculate， 我原来的这个点的 modulus 就是不一样的。OK， 我这个就是我新的数据下面的 modulus。这个明白了吧？啊，所以给了你一个反馈的过程。你说我就想看图，那就是图。想看点，你就把一个点一个点，这个点都可以重新 export 出去，让它营做一个单体的，你们就不用再去 ramp 了。这时候就不用再回去 ramp 了，它已经给你记录下来了。这个记录在哪儿呢？就是在这个 PeakForce QNM 的时候下针的时候，就是下针的时候，下针到这里要把这个打开，才能够都给你记录到这个 Pascal。如果说你没有打开这个，你用的是这个 capture， 对不起，你是没有返回的过程的，只有你原来的数据上面的那个 modulus， 啊，你就改不了了。假如说你
这个
你等一下给看到你就可以看到，当你下到样品表面以后，这个就 active 了。你要把这个打开，这个上面出现了一个小力曲线的时候，然后呢，你再 capture， 这个 capture 跟其他的那个 capture 呢不一样，这个不能 capture now， 这个一定要从上到下 capture 一个方的。一定要 capture 一个方的一个整个的苔藓 ，OK， 他没有说那个你采半个那种啊，这个就不能采半个了啊。金星准备好了还是怎样？很难。看，咱们现在力曲线很正常是吧？图也很正常，我现在找了5个微米。OK， 你看到这个就可以开始采图了，对不对？好，你如果只是按这个的话，你这样采图，从上到下采图的话，只有这8个通道的图，看你改不了任何数据了。对，然后呢，你这么采图，你看我这个时候采图。这个时候的采图，我是可以 about 它，我 capture now 的。那我就扫了这么点，我就 capture 这么点，是可以的。但是如果你这时候只有这个图，只有一个一个那个 SAP 的图，对吧 ？OK， 它是只有图的，所以你打开看，这个地方是没有力曲线的。OK， 那这个上面是没有任何力曲线的，只有这几张图。OK， 改不了的啊。哎，你把这个东西打开，你看到这个上面就出了一个小尾巴，看到吗？你这时候去 capture 的时候，它让你从头到尾，因为你改了嘛，看到没哈？所以你就从头到尾重新扫。你这个 capture 的时候，到时候它会给你2个图，一个是 SAP 的图，还有一个点 PFC 的图，那个是包可立体线的。
然后就可以输入
哎
跟数据的
对，那是原始数据就都有了但是这个呢，你没有办法 capture now， 你把这个去掉它，这个 capture now 是不包括历史线的，所以必须从头到尾。这个明白了没有？必须从头到尾啊，收 PFC
等于这就是 scan 里面
啊，这是 scan 里头，
那我
，scan 里面它也把历史线都给了你，看到没？它每一点历史线它都已经给你记下来了，你就没有必要再去 run 它了。
哦，那就不用再搞 ramp
啊，对啊，你有了每个点了，你就不需要搞 ramp 了。
我们明天继续吧。
明天继续吧，好好，
对，
那可以啊，好，好。明天上午下午都做明天上午下午都是做实验咱明天上午下午不讲课，或星期五才讲课呢，星期五去课时，明天都到这儿来，OK
老师，这是昨天我问你有个软件批量处理我
我回头发给你，你到时候加我微信，我回头发给你你把那个拿出来吧，那个
等我吃饭去。
对，我看一下来。
就是那个软件可以直接做那个。
对，做那个批量处理，那个历曲线的批量处理可以。
它出来之后是可以自动手控制吗？
他会把数据都给出来，你自己愿意这边。对，